If you haven't watched Neil Turok's lecture in Rethinking the Foundations of Physics, the debut episode, then click the link in the description before watching this Q&A. What is your gripe with the multiverse concept? And also, what do you make of the concept of a wave function of the universe?
Great questions. The multiverse, to be honest, I'm a fairly open-minded person. I'm not dogmatic about anything. I think science is precisely about discovering what's true, and the worst thing you can do is bring too many preconceptions. As I said, my fundamental belief is that the universe teaches us things. We need to be willing to learn. And you don't learn. If you come to something with a fixed idea, you don't learn. So I am open-minded. I wrote a paper with Stephen Hawking, essentially about the multiverse. Stephen liked the multiverse idea, but
why?
Yeah, it's hard to ask him why. I never really took to it, but as I say, I was sort of open-minded, and it looked like I was willing to explore string theory for as long as it looked like it was leading us in an interesting direction. And string theory sort of indicated something like a multiverse. And so I thought, okay, well, let's try it out, But my problem was that I am only interested in theoretical physics to the extent that it describes nature. Okay, that's the only reason I'm interested in it. I'm not interested in it as a mathematical exercise. What I am interested in is this extraordinary fact that human beings, who after all are, essentially monkeys who have evolved out of bacteria in the primordial ooze, somehow, through some means or other we don't yet understand, we develop the capacity to understand the whole universe. It is just completely insane. And I find that so profound and so wonderful that I'm very happy to devote my life to try to, explore this fact about the universe, that we have the capacity to understand it. It's amazing and it's bizarre. So if you like, I view my work as homage to this fact.
Okay.
That for some reason human beings have the capacity, and I shouldn't say human beings as opposed to animals. I think animals and humans essentially learn in very similar ways, and we all have this ability to learn about the world. So I don't want to separate humans from any other form of life.
Sure.
I rather liked your, what was his name? Bernard Kastrup, his view.
Oh, Bernardo Kastrup.
Yeah, I rather like that point of view that, we are consciousness and we're all individual aspects of that. As a philosophical view, I kind of like that. So I'm not a materialist.
Interesting. Is that common in your colleagues?
No, but I believe in exploring, and that's what motivates me. When string theory started to make excuses, and I view the multiverse as the biggest excuse of all time, okay, we can't predict this universe, but we can predict a billion others, I began to lose confidence. And I lost confidence because you're no longer predicting anything. And if you can't predict anything, you can't really check your ideas. You may be just engaging in a fantasy. That's a terrible danger. If you're a theorist, the danger that you're just deluding yourself is enormous, right? I mean, that is the most likely thing. Probably I am deluding myself. Probably we're all deluding ourselves in thinking we can understand the whole universe. And it seems like the ultimate chutzpah, to say, I can understand the whole universe. So I think the only chance that we are not deluding ourselves is if we really pay attention to facts. Now facts are always difficult because sometimes they're wrong, the experiments go wrong, they're misleading, etc., etc. They have a lot of issues. However, it is our most reliable source of information. And I think we have to take it very, very, very seriously. So I was interested in the multiverse basically because string theory seemed an effective theory of quantum gravity, and it seemed inevitable within string theory. But as soon as this possibility of a much more constrained, predictive, and I would say principal theory came along, I would grab it with both hands. And I think any theorist would be crazy not to. And what worries me, okay, our theory, as I've emphasized, is very early stages, baby steps, very encouraging ones, but nevertheless baby steps. We're nowhere near the level of string theory. But I think we have very similar things going on. Namely, we have our whole principle is theoretical consistency. And we see clues both from the mathematics and these 36 fields and from the behavior of the real universe. We see clues that are guiding us towards very deep principles, this conformal symmetry, which resolves the Big Bang. So these are very powerful principles. So what I think of at the moment is what we are trying to do, Latham and I, essentially, and other people slowly getting interested, is recreate string theory, but with a different set of assumptions. One is there are 4 dimensions, that gravity is a theory. String theory essentially postulates that gravity is a sort of spin-off byproduct. The fundamental things are strings. We say no, 4-dimensional space-time is the thing you have to quantize. And it's difficult. So we're trying to create a realistic string theory. Basically, that's the way I view it. With the minimum of ad hoc theoretical ingredients. And so, it's hard to be objective, but I think if I was a string theorist today, I would be extremely worried that the work I'm doing is irrelevant to the real world, because there's so many ways in which string theory does not succeed in describing the real world. And I would be looking, if not at our approach, for other approaches that are similarly economical, principled, predictive. I'm quite happy with this line of research. Quite frankly, it's a relief that not more people are interested in it, because we don't have to keep looking over our shoulders. So I highly recommend it to young physicists in particular. Find something which is sort of seems to have a compelling internal logic, and pursue it to its logical conclusion. That's the very best thing you can do as a theorist.
And what do you make of the concept of a wave function of the universe?
Oh, thank you. So Stephen Hawking, of course, whose feet I learned at, was a big fan of the wave function of the universe. Personally, the person who invented it was, there were 2 people. John Wheeler, who I was very privileged to know at Princeton. He was a professor at Princeton when I was junior faculty. I used to drive him home after the physics colloquium because he was rather old and not allowed to drive anymore. So he was an absolutely inspirational figure and just a wonderful human being.
I'd like to ask you questions about Wheeler another time.
Okay. So John Wheeler, I had the privilege of asking him questions. Why is the universe this and like that? And he had very sort of, what's the word?
Opinionated?
No, not opinionated, but oracle-like.
Okay.
He was an oracle. Okay. So he would say very simple things which left you scratching your head. And then 20 years later, you realize, oh my God, he was right. Okay.
Interesting.
So he invented the word black hole. He invented wormhole. He invented wave function of the universe. Now, and he had a very, very deep picture of what this meant. The other person who invented it was Bryce DeWitt. Now, Bryce DeWitt was the most technically proficient theoretical physicist in the world in the 1960s. Okay, extraordinary person. I had the privilege of seeing him when I was a undergrad at Cambridge. He came to Oxford and gave a lecture, and I was there. He wrote very, very few papers, and the ones he wrote were absolute masterpieces. So Bryce DeWitt and John Wheeler got together to discuss the Hamiltonian constraint in GR, rather a technical thing in the classical theory, and its quantum realization. And they came up with an equation which was supposed to be the analog of the Schrödinger equation, but for gravity. Now, Wheeler was very excited initially, called it the wave function of the universe, and so on. DeWitt thought more and more about it and came to the conclusion it was nonsense. Okay, so DeWitt, a few years later, wrote a phrase saying, "This is the most ridiculous equation in physics." And the reason for that is it's a partial differential equation. That's okay. Like the Schrödinger equation, you have d by dt and d by dx in the Schrödinger equation. So that's all right. It's a partial differential equation. The problem is it is infinite order. Okay. Namely, the Schrödinger equation, 1 d by dt, it's first order in time. It's second order in space. The Wheeler-DeWitt equation for gravity is infinite order, PDE. You don't know what the boundary conditions are, and you don't know which solutions. You would need an infinite number of boundary conditions. And if you just take this equation at face value, there's an infinite number of solutions. So, who knows what it means? It's, I would say, just like the Schrödinger equation, it's a useful technical device, but it doesn't really give you much insight into what the initial condition was at the Big Bang or anything like that. Now, Hawking he tried to define the no boundary proposal. And Hawking's proposal was the motivation for our proposal of a mirror. Hawking had a kind of even more beautiful proposal, which is that you take four-dimensional space-time and you round it off at the beginning. So there is no boundary. There's no beginning. It's just, so imagine a sort of rounded surface, and we live on the final edge. And so he called it a no boundary proposal. This was rather nicely formulated in a path integral way. But Hawking then tried to use the Wheeler-DeWitt equation to examine the path integral, because path integrals are rather difficult. They're harder than the Schrödinger equation. In quantum mechanics, Schrödinger solved the hydrogen atom using his equation. But to solve the hydrogen atom in the path integral took 50 years, or probably more, 50, 60 or 70 years. So it technically was just much more difficult to use path integrals. So nevertheless, Hawking formulated his theory as a path integral, and then he tried to use the Wheeler-DeWitt equation. When he did that, he sort of cheated. He put in some boundary conditions, but they don't really make any sense. And so, yeah, I would say the wave function of the universe, if you literally deal with the Wheeler-DeWitt equation, you better find a way of dealing with infinite order partial differential equations, showing there are sensible boundary conditions, showing that there are unique solutions, all of that. If you want to deal with path integrals, which is more geometrical, the sum over geometries, is a more intuitive geometrical thing, then, deal with path integrals. I think all of these papers on the wave function of the universe, and there are tens of thousands of papers now, are not really making much progress. That's my view. I mean, they're just kind of recycling the same old ideas, which haven't really led anywhere. The reason I lost confidence in Hawking's proposal is it gave the wrong predictions. Hawking's proposal did not produce a universe like ours, whereas our mirror hypothesis does. Our mirror hypothesis predicts a flat, spatially flat universe, homogeneous and isotropic, which looks like ours. So I would say it's just an alternative to Hawking. Just like Hawking, we have no extra inputs. You see, what I think doesn't really make sense philosophically, or at least I shouldn't say philosophically, maybe it does make sense philosophically to have a creator. But what doesn't make what is not very appealing, let's put it that way, scientifically, if I want a predictive theory, I do not want the freedom to input stuff at the Big Bang. I want everything to be self-contained. I'm going to write down some laws of physics, and I want those laws to define their own starting point. Okay.
Mm-hmm. So usually laws are seen as distinct from boundary conditions.
Exactly. So Hawking's hypothesis, the no boundary proposal, had the laws of physics, namely Einstein's theory of gravity, define its own starting point. That was what was so elegant about it. The mirror hypothesis is the same. You say the laws of physics and the CPT hypothesis, that the universe doesn't violate CPT, those define the boundary condition at the Big Bang, and then there's no freedom in what you input. So, yeah, all Latham and I are doing is try to minimize the number of assumptions that you make and see how can we explain what we see with the very least and hopefully most appealing assumption, most attractive assumptions.
Yes. Now, how do you explain that our universe isn't conformally invariant? So,
right,
you
great
can just
question.
look around you and it's not. So there must be something breaking it.
Yes, absolutely. So, in order to resolve the Big Bang singularity, you need this conformal symmetry, right? I mean, that seems very intuitive. If space shrinks to nothing, the only way to make sense of that is if that is just an artifact of your description. You've somehow used variables which shrink to nothing. You can map the problem to another problem in which space doesn't shrink to nothing, shrinks to a finite mirror, and now you have a coherent description where the equations work and so on. So it seems that, at least from our point of view, you have to have conformal symmetry to have a sensible description of the Big Bang. That does not mean you need conformal symmetry today, because between the Big Bang and today, you can break conformal symmetry. Okay, so there needs to be a theory of conformal symmetry breaking. Now, we're very familiar with this in the Standard Model. In the Standard Model, there's a symmetry group called SU2, weak, which rotates neutrinos into the electron, for example. It's an SU2 symmetry, and the laws of physics have that as a fundamental symmetry. Nevertheless, that is what we call spontaneously broken by the Higgs field. When the Higgs field switches on, it sort of picks a direction in this SU2 symmetry space, which defines the electron and the neutrino. An electron is the direction along the Higgs field, neutrino is the orthogonal direction. And so the notion that the laws of physics do have conformal symmetry, but that symmetry gets spontaneously broken, this is an extremely attractive hypothesis. Having said that, physicists have been working for 50 years, right, on various ways to break the conformal symmetry. I can put it a different way. You see, the Standard Model, if I switched off the Higgs mass, there's one parameter in the Standard Model which breaks conformal symmetry. Only one. And that's the mass of the Higgs field.
Mm-hmm, right.
It's the only parameter with dimensions of mass. Okay, and it's how you get the mass for the Higgs field. Without that parameter, the rest of the theory is conformally invariant. That's actually a consequence of renormalizability. You know, renormalizability is a very special property in four-dimensional theories, and it requires dimensionless couplings. And when you have dimensionless couplings, you have conformal symmetry. So if you want to explain explaining the breaking of conformal symmetry is actually explaining the origin of the Higgs mass. These things are very tightly related. What is very exciting, I didn't mention it in my talk, but there's a new development, very new development, which is a new idea for explaining the Higgs mechanism without inputting the Higgs mass.
Okay.
Okay. And this is work by somebody called Ramachki. He's essentially a quantum field theorist who works in lattice gauge theory and also high temperature nuclear matter. So a real physicist. It's not a string theorist. And he has pointed out, you see, I need to explain a little bit more. How do we explain the origin of mass? Okay, and mass scales. Now, in one case, in quantum chromodynamics, the explanation is very natural. Why do I say that? You see, quantum chromodynamics, the theory of a strong force, is what's called asymptotically free. It means that as you go to higher energies, the coupling constant goes to zero. As you come down in energy, the coupling diverges, and the theory becomes strongly coupled. You can say the following. Let's imagine I fix the strong coupling constant to some number, like 1/30th. That's what you get by extrapolation, at the Planck scale. And so the very, very high energies at the Planck scale. And I now ask, what is the scale at which it becomes 1? So it's a 30th at the Planck scale. And I ask, what energy scale does it become 1? And that energy scale is the scale of the mass of the proton. Okay, so in other words, the proton mass is only 1 GeV, whereas the Planck mass is 10 to the 19 GeV. But that difference is not hard to explain. The reason it's not hard to explain is because the coupling constant runs only logarithmically with energy. And log of 10 to the 19 is only about, 40 or something, 35 or 40. And so logarithmic running of couplings gives you a very natural explanation of enormous mass hierarchies. So in the case of QCD and the mass of a nucleon, the mass of the proton, there isn't a fine-tuning problem. You just say, okay, for some reason, the coupling constant, the alpha 3, the fine structure constant for the strong interaction is about a 30th at the Planck scale. When I come down in energy scale, when I hit 1 GeV, it's strong. And that defines the mass of the bound states of particles, the proton. So this new explanation of the Higgs mechanism is like that. It claims that there's a way to formulate the theory where the relevant where there's no mass scale put in, all the mass comes about because of the running of coupling constants with energy scale, which is a quantum effect. So another way of saying it is that all masses are quantum in origin. And so this new work shows that, claims to show that. It's not quite complete. He hasn't actually predicted all the details. He's just made it plausible that it can work. It shows that the Higgs mechanism and the Higgs mass can be explained very naturally as being due to quantum effects in a certain kind of model. That kind of model is probably the simplest quantum field theory you can define. It's called lambda-Fiden fourth theory. And what I've shown recently is that model maps perfectly to our dimension zero scalars. Okay.
What do you mean it maps perfectly to them?
Well, it's quite technical, but so I'll just say a few words. They may not...
Sure. You can also say what the name of the paper is so I could put that on screen.
This is not written up yet.
I see. Okay.
This is in very recent work. We haven't written this up. So this was just last month when I was at Perimeter.
Sure. Give the cliff notes if you don't mind.
Sure. I mean, it's still secret, so...
Oh, okay. All right. Then off air, we'll talk about it.
Yeah, I think so. I don't want to say too much about it because my students are busy working on it and they need this. They need these papers.
Of course, of course. Okay, so then how about this? Do you think the Higgs is a fundamental particle?
In our explanation of the cancellation of the vacuum energy and the conformal anomalies, we cannot have a fundamental Higgs.
Interesting.
The Higgs field cannot, it is inconsistent. This cancellation mechanism says there are no fundamental Higgs. It also says we have to introduce 36 dimension zero fields. The logical inference from those two facts is somehow the Higgs field must be made of the 36 dimension zero fields. It must be a composite. Okay? And this recent work by Ramachke is very exciting because it points to that being possible. So I think we are on the verge of a reformulation of the standard model based on dimension zero fields without mass parameter being needed to be stuck in by hand. This would automatically solve what's called the hierarchy problem. The hierarchy problem is the difference between the weak scale or the proton mass, if you like, in more simple terms, the difference between proton mass and the Planck mass. It differ by 19 orders of magnitude. Where did that come from? This would be naturally explained if all mass scales arise in the same way due to the running of couplings, which is a quantum effect. So I think we're seeing hints of a solution of the hierarchy problem. By the way, the hierarchy problem was the main motivation for looking at supersymmetry. Mm-hmm. Much less compelling picture with all kinds of extra particles and parameters and assumptions. And so supersymmetry became big precisely because people thought it might solve the hierarchy problem. What we're seeing now is a far more economical solution, which basically involves sort of tampering with the vacuum in quantum field theory using these funny dimension zero fields. But if we're right, this is going to revolutionize particle physics.
You mentioned that you're not a fan of data fitting.
Yes.
And then you also mentioned that there's the introduction of these 36 fields.
Right.
So do you see that as a form of data fitting?
No. What happens is, it's a very curious numerology that when I say there are 36 fields, we have to explain the number 36, and we don't yet have a explanation for it. So what we found is the strange coincidence that basically the vacuum energy per mode of the fields in the vacuum, so every quantum field in the standard model has an infinite number of modes. You can think about these as waves of different wavelengths and with different direction. So there are infinite number of these modes. Every mode has some vacuum oscillation and contributes some energy. So in the standard model, the energy in the vacuum is just basically some overall number times a sum of integers. I get some number times the number of spin zero fields, another number times the number of spin half fields, and then the spin one fields. Similarly, with the violations of local conformal symmetry, which I mentioned, this is called the conformal anomaly. It's also a sum of integers with strange coefficients. Okay, so all of that is a consequence of quantum field theory. That if you put there are actually three of these kind of violations which happen, and they're all sums of integers. So you get three sums of integers with various coefficients, including some fractions, and you want all three sums to be zero. We discovered that if we add these strange dimension zero fields, and if we add precisely 36 of them, then all three anomalies cancel the vacuum energy and two independent contributions to these violations of the local scale symmetry. So suddenly we get this much more beautiful theory. It demands 36. There are no free parameters, right? It requires 36. Now, where did the 36 come from? There are various suggestions as to where it comes from. 36 is the dimension of a group. In fact, two groups, simple groups. One is SB8 and the other is SO9. These groups are related to twistor theory. Twistor theory has a sort of bigger version, which involves SP8. And what's very tantalizing is that maybe, once we understand that connection better, we'll see that we're forced to 36, preferably by gravity. We want to see that gravity does look much nicer in its twistor representation. There are no new parameters in the twistor representation. The twistor representation may then lead us to this bigger picture in which there are 36 fields. Coincidentally, I should have mentioned, twistor theorists who are much more on the mathematical end than we are have shown that in the Feynman path integral for gravity, they need to introduce 36 dimension zero fields to make sure that the twistor path integral equals the gravitational path integral. And the amazing thing about their result is it's not perturbative. You see, our result is only true for free fields. It's the most naive possible calculation. Their result is true to all orders, right? These are serious mathematicians, and they've shown that introducing these dimension zero fields cures these problems non-perturbatively. Okay, so that's very spectacular. So we're hoping that our work ultimately connects with theirs. If it does, then the number is actually going to be fixed. It's not a free parameter. So that's still to come. Now, having said that, the way we treat the 36 fields is naively, if I've got 36 fields, I'd have a huge number of parameters and coupling them all. I could write down let's say the kinetic term and then a potential term with 36 different fields. I'd have a very huge parameter space of potentials.
Uh-huh.
The way we use these fields, they are not allowed to have a potential. Okay, so that's not possible. And the way we use them is we treat them all equally. So when they contribute, it's 36, all giving exactly the same. That's, as I said, there are assumptions in our calculation. We always make the simplest assumption. And that assumption is that all 36 fields contribute equally. So we've tried to be as minimal as possible with this theory. It doesn't mean that, that there aren't free parameters for sure, because this is still under construction. What we hope is that as we understand it more and more deeply, we will see that there are constraints which come in, which force you to make these choices. And, we're hoping that ultimately there aren't any free parameters in this game. Of course, that's a very ambitious dream.
Yes, right. So this is the Boyle-Turok model, correct?
Yes.
That's what people can search if they want to hear more.
Yes, they can just look for my name, Latham Boyle's name, and all of our papers on the archive.
So the 36,
yes,
there are also 36 parameters in the gravity spin connection.
Correct.
Now, is that a numerical coincidence?
Other people have pointed this out, that there are many formulations of Einstein's theory of gravity. Right? The original one, you have a metric with 10 components, and then in a rather ugly way, you have a Christoffel connection, which has 40 components. Okay, so you have all these different fields, in fact, in Einstein's theory of gravity. Now, what happened after that is other people discovered different formulations of gravity, which are somehow more economical and more beautiful, more geometrical. And there are many of these. One involves Vierbeins and spin connections. And in fact, you have to go to that representation to describe fermions in gravity. You have to use Vierbeins and spin connections. But these theories have different numbers of fields than Einstein's formulation. And these, as you mentioned, there's a particular formulation of gravity called a Plebanski formulation, which emphasized that you could write down Einstein's equations very, very beautifully if your fundamental object was not the metric, but was an antisymmetric two-component tensor called a B field. And this B field is an antisymmetric tensor with two indexes, each one can run over 4 values, has six values. This B field has both space-time indices, both a mu and nu index, sort of coordinate indices, and also Lorentz indices, also antisymmetric. And so the 6 of one and 6 of the other, and you get 36. So people have pointed out that maybe the 36 is somehow telling us about this formulation of gravity. That's very tantalizing. We don't know whether that's true. I think the connection with twistors is also a hint that that may be a better formulation of gravity. So, we're trying to do something very difficult here, which is write out a consistent, quantum path integral for gravity. And certainly the naive one is not the full story. So we have to find the right variables in which to write that, the path integral for gravity. And as I say, there are a couple of hints that 36 is going in that direction. But so far, these are just kind of numerical coincidences. We're not clear what to make of them.
Where does dark energy come from?
Well, it's a good question. I mean, as you know, as I said in the talk, it's the simplest form of energy there is. It's just uniform in space, uniform in time. So
you view it as another constant, another knob to fiddle with?
I'm not happy about that, but that is the current state of thing. In the part of my talk I didn't give, I was going to talk about thermodynamics. And the thermodynamics of the universe, you see, I think that the most profound explanations in physics are ones which use thermodynamics. Okay, entropy. Entropy is the most profound concept in physics. It's like, how many ways can you arrange something, right? More generally, you can say entropy tells you, if I have limited information about the world, and I want to know what's going on in the world, what I do is maximize the entropy. I say, what are the greatest number of microstates of the world compatible with what I do know? And then most likely the world will be in one of those states which maximizes the entropy, right? The most likely states are the most numerous. So the notion of entropy, I think, is sort of beyond the laws of physics. It's saying, given probabilities, given that nature is probabilistic, and we think quantum mechanics is probabilistic, given that the laws of physics are fundamentally probabilistic, the laws of probability kind of supersede everything else. And so thermodynamic explanations are always the best ones, because basically they say, no matter what you do with the laws of physics, you're going to get the same answer. Okay. So we have a new thermodynamic explanation for the geometry of the universe, based on Hawking's ideas and our mirror boundary condition, et cetera, but it is thermodynamic. And you ask me, what about lambda? So what is lambda? What is the cosmological constant? Now, in thermodynamics, the basic idea is you constrain certain quantities. So let's say I've got a box of gas, certain number of particles, certain amount of energy, and I find the maximum entropy state, which is the equilibrium one, where all the particles are essentially evenly distributed and they've shared out all the energy and so on. But you need to impose the right constraints. So in the case of particles in a box, it would be all the conserved quantities, number of particles, total amount of energy, actually the total momentum of the particles, the total angular momentum. You can constrain those things. Now, in gravity, everything is geometrical, okay? And that makes the theory very unique. You say, how do I define the theory? Well, I have to deal with geometrical quantities. Probably the most obvious geometrical quantity you can think of in a four-dimensional space-time is the volume, the total volume of the space-time, right? I integrate over space and time, and I get a four volume. So now you ask, what is the cosmological constant? Well, it is the term in the action for gravity which multiplies the four volume. So lambda multiplies the four volume. If I do thermodynamics on gravity, lambda is analogous to temperature or chemical potential. What is temperature? Temperature, it says, when I do thermodynamics, I take the energy in the system and I multiply it by 1 over kT. So I have in my statistical ensemble, I've got the Boltzmann factor, e to the minus energy over kT. The best way to think of temperature, it is just 1 over kT is the quantity multiplying the energy in the statistical ensemble. And I just dial that to get the average energy in the box. So you can say you would dial the cosmological constant to get the four volume of the universe. Okay, that's the way in which it occurs in gravity. So essentially, it's saying that if I want to describe particles in a box, I need a temperature. I just say, if I ask you what's the most likely configuration of particles in a box, and I don't tell you the energy and I don't tell you the number of particles, you can't say anything. You need some information.
Yes.
So I can say a box of gas at temperature, 30 degrees centigrade, and with a certain density of particles, certain number of particles in the box. Then I've defined it. So it appears the way the cosmological constant enters physics is in the same way as temperature does, or chemical potential, which we use to describe the number of particles. And it controls the volume of the universe. Now, then it's up to you what you fix and what you predict. So you can fix the number of particles, or I could say, no, I've got a box of gas at certain pressure and temperature, some measurable things. Then predict how many particles there are. Predict the energy in the box. But you need to know a certain number of things to predict other things. Lambda might be just one of those things you need to know to predict other things. When we calculate the entropy of cosmology, it's very tantalizing. We find that the entropy is greater the smaller lambda is, and the thermodynamics only makes sense if lambda is positive. So basically, roughly speaking, it predicts that the cosmological constant is as small as it can be, but it has to be positive. And that's very compatible with what we see. But it's only halfway there. We need to now understand what are the other constraints. Should we be fixing lambda? Should we be fixing the four volume? Maybe the four volume is quantized. We haven't put that in yet. When you quantize the four volume, maybe lambda only takes discrete values. So I think we're seeing glimpses of the role of lambda, but at the moment we don't really understand what it is or how to use it. We can fit it to the universe. That's not a theory. That's just a fit. But what you hope is a sort of deeper understanding will lead you to understand the value. But ultimately, the value, so this may sound a little anthropic, and I'm not anthropic. I don't like the anthropic principle because I think it's very abused. But I'm not averse to selection effects. There are selection effects. We live on the surface of a habitable planet. That's not a surprise. That's where we evolved, and so it sort of seems foolish given that there are, 100 billion stars and 100 billion galaxies and 100 billion stars in each galaxy, and many of them have planets. We don't usually say, predict why the Earth is habitable. I mean, we're here because it's habitable. So that's fine. But you shouldn't. You see, when people use the anthropic principle in cosmology, they do. I think they do it in injustice because they don't know what. Technically, you say that they don't know what the measure is. They don't know how much weight to assign any particular cosmos. And then what they typically do is say, "Oh, this one looks like the one we see. The universe had to be like the one we see because we're here, okay?
Mm-hmm.
And so maybe it has to be like that just because we're here." And that gets them off the hook as actually explaining anything at all. But I don't want to do that. I want to understand as much as we can about the universe with as few assumptions as possible. So I don't mind there being a selection effect at some point.
Yeah, I'm not understanding the difference between the selection effect and then what the people who have a variety of values, and then they say that, well, we happen to find ourselves at one of these values.
Right.
And it's because that value is, well, I don't see the difference.
Imagine you have a multiverse, right?
Sorry, is it the case that in the planet case, we have a measure?
Yes.
Because we can see how many other habitable stars there are, or habitable planets surrounding a star there are?
No. In the planet case, we have not seen any other, so far, any other planet that's remotely habitable. Right? Maybe there's some recently. But in the planet case, we have observations indicating that it's really unusual for life to arise, right? I mean, certainly it seems there's no other life in the solar system. And when we look at other stars and planetary systems, typically they seem not to be suitable for at least our kind of life. So it seems that life is rare, right? And maybe very, very rare. For all we know, we're unique in the observable universe. Now, what people do in the multiverse is, I think, take that much, much further and say, I've got this 10 to the 1,000 universes in string theory. Maybe only universes like ours are habitable. And therefore, all the features that I can't explain of our universe using string theory, I'm going to explain this way. So basically, it's just an excuse. It's a way of letting yourself off the hook that you will never explain the value of the cosmological constant. You will never explain, various other cosmological parameters, just because you're saying, oh, there had to be that way, because otherwise we wouldn't be here. So I think that's a non-explanation.
I see.
What I believe there may be, and I think all the indications are, there may be an explanation which is way better than that. Okay, which basically says that in a certain category of well, let's see. You see, okay, now I'm going to get very spacey and refer to Bernardo.
Bring it on.
So Bernardo says that, reality is essentially a manifestation of consciousness, right? And that the world at a deep level is all about information. and this unified consciousness somehow processes this information, right? So I think that's a very appealing perspective. It's not very materialistic, right? And as he rightly said, it's not very scientific because at this point we don't know how to test it. But we can't disprove it either. So now, if you adopt this perspective and you say within this realm, however consciousness works, it is possible for things like universes to emerge if the laws of physics are quantum mechanical, are actually just probabilistic. There will be a number of possibilities, and given that what did he call it? My dissociated, I'm quoting his words. Given that my dissociated consciousness, right, has only partial awareness, maybe universes like the one we see are the most probable. Now, how do we even test this? How do we try to turn this into science? I would say the best way we do it is by taking the laws of physics we know, push them as far as we possibly can, use analogies, use mathematics, try to make a logical framework where we calculate probabilities. And our calculations of entropy and gravitational entropy are very much going in this direction. It may be that in this space of information processed by consciousness, certain values are preferred, most likely. If it is a thermodynamic explanation, that will be fairly independent of the laws of physics. Maybe it probably will depend on gravity in some way, but not on the fine details. And I think it may be that we can at least approach such an explanation of the cosmological constant, of the basic structure of space-time. And that seems to me a very fruitful way of exploring, So instead of posing the question like, I've measured this number lambda, it's 10 to the minus 20 and 120 in Planck units.
Okay.
What a massive puzzle that is. Don't try to just predict the number. Try to predict everything and use all the information we have. Try to make your framework compatible with everything we see. And as you succeed in refining and further formalizing the unified laws of physics with all the observations we have, as you succeed in doing that, if nature is unified, you will see these unifications happen. So maybe we're right. Maybe we have explained the fluctuations coming out of the Big Bang. That's great. Now that gives us confidence in the vacuum, right? How do we understand lambda? Well, lambda is the energy in the vacuum, right? That's what lambda is. We've made a step forward to it because we've canceled infinity. We had a terrible paradox that the vacuum energy was infinite. In our new theory, with these dimension zero fields, at least the leading infinity is canceled. Now we're dealing with finite numbers. So let's just keep developing that, keep developing the machinery and the formalism, trying to remove kind of logical inconsistencies as we go. And maybe this will actually end up converging on the lambda. If lambda currently, in our current perspective, takes this ridiculously small value, right? But as I explained, if things only depend logarithmically on energy scale, you can get very large numbers appearing out of very modest numbers. Equivalently, you can say if I exponentiate 30, I get a huge number, right? But it's only because you didn't understand the logarithm that you thought this is ridiculous. So we do know many things in physics change logarithmically. Most likely, the log of lambda is the physical parameter. And if the log is the physical parameter, then there's no real puzzle about it being so tiny. And perhaps the log had to take a particular value, in order for the physics to be consistent. So I wouldn't claim we are near to explaining why lambda is so small. What I would say is we're developing a framework which is unified insofar as it goes, it is complete. It accounts for everything we see. It accounts for all the known laws of physics. And yeah, let's push it further. I wish there were many other frameworks like ours competing. That's healthy science. What I fear at the moment is that string theorists have essentially gone off into mathematics land, and they're busy exploring n=4 super Yang-Mills and all kinds of ADS5, cross S5, all of the sort of totally unrealistic universes. And yeah, what I worry about is they are never to return. When you take one wrong turning in theory land, and if you're dogmatic, you will never come back. I mean, that's the biggest danger in the whole field of theoretical physics, is you make one mistake. It's so ambitious, to explain everything, that if you make one mistake, if you insist on sticking to that mistake, you're never going to come back to the right picture. So I think much more likely to me is if you're adaptable, if you quickly realize when you've gone wrong and don't accept it, change course, that's the way to make progress in the field. And yeah, that's what we're trying to do. But rather few people are trying to do that.
Neil, I appreciate you spending so much time with myself, with the audience here. And I appreciate you being the inaugural talk on the Rethinking the Foundations of Physics, What is Unifications series.
Thank you.
And people who don't know what that is, there's a talk that you can go click on that gives a lecture that Neil just gave, approximately 1 hour in length. And it's a fantastic talk that goes over the mysteries of the universe explained economically in a simple manner. So thank you, Professor.
You. You're very kind. Thanks a lot. It's an absolute pleasure.
Firstly, thank you for watching. Thank you for listening. There's now a website, curtjaimungal.org, and that has a mailing list. The reason being that large platforms like YouTube, like Patreon, they can disable you for whatever reason, whenever they like. That's just part of the terms of service. Now, a direct mailing list ensures that I have an untrammeled communication with you. Plus, soon I'll be releasing a one-page PDF of my top 10 toes. It's not as Quentin Tarantino as it sounds like. Secondly, if you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for theories of everything, where people explicate toes, they disagree respectfully about theories, and build as a community our own toe. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in theories of everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, toe listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/CurtJaimungal and donating with whatever you like. There's also PayPal, there's also crypto. There's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on Toe full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.